Welcome back. Now I'm super excited for this video. It's going to be a full-on one, but I think you're up to the challenge. We're about to build our first end-to-end convolutional neural network. However, before we jump into that, I just want to put a little tidbit here. I added this to the last video, just continuing off. We put this little key emoji here for write down things that we should note. As we've discussed before, many machine learning models, including neural networks, prefer the values they work with to be between 0 and 1. Knowing this, one of the most common pre-processing steps for working with images is to scale, also referred to as normalize, their pixel values by dividing the image arrays by 255, since 255 is the maximum pixel value. Now, that's just a follow-on from what we did before to finish off that image array, normalizing all of the red, green, and blue pixel values. So without any further ado, let's get into an end-to-end example. Now, as I mentioned before, there will be a few things in this video we haven't quite covered before. However, I'm going to show you the end-to-end example. This is where we're going to end up, and then we're going to work backwards from there. It'll all make sense in a few videos' time. Let's have a look. An end-to-end example. Let's build a convolutional neural network to find patterns in our images. More specifically, we need a way to load our images, pre-process our images to get them into a state like this, because doing this one by one would take far too much time. Pre-process our images, build a CNN to find patterns in our images, and then we need to compile our CNN and then fit the CNN to our training data. So let's do it. What do we start off with? We're going to need TensorFlow, of course. Import TensorFlow as TF. And we're also going to need a new module we haven't quite seen before. Remember, I gave you a warning. There will be a couple of things we haven't quite seen before, but as usual, we're going to step through it by writing code. So image data generator. You may be able to guess what that means. So let's start off how we always do. Set the seed, TF, random, set seed, 42. And now we're going to set up the data preprocessors. So preprocess data, get all of the pixel values between 0 and 1. This is also called scaling / normalization. Wonderful. And to do this, we're going to set up 2 instances of image data generator. And we're going to pass it a parameter here called rescale. And it's going to be 1 divided by 255. Let's just run this so that we can view the doc string of this. What does it say? Here we go. Generate batches of tensor image data with real-time data augmentation. Now, we haven't covered what data augmentation is, and we haven't really covered what batches of tensor image data is. But we'll see what this looks like in practice, and then we can go through. If you want to go through the documentation before we keep writing the code, feel free to pause this video and come back. But I'd like to encourage you to just continually write code, see what the outputs of your code are, and learn by doing. So now we're going to import data from directories and turn it into batches. We have seen the word batches before, or batch size before, but that's on the keynote. I'm going to finish all this code first before we go back to the keynote. So I'm going to set this up as train data, and I'm going to bring in the instance of image data generator we just created. So train data.flow from directory. You might be able to guess what this does. Now we need to pass it a training. Oh, you know what? We've missed a step. We need to tell TensorFlow set up paths to our data directories. Now, there's a couple of ways we could do this. We could grab this and we could copy the path using that. So for one, we might do that. So this is the training directory of pizza steak. So I'm going to copy path and I'm going to write this down here. Train dir equals paste that. this is the same as, we'll go here, test dir equals, you actually don't need this content at the start there. So we can just do it like this as well for the test directory. Wonderful. And then we're going to pass the train dir here. So see what we did? We just took this variable, training directory with all of our training images, and passed it into train data. And this actually needs to be train data gen because we're taking that and putting it here. So this is a flow from directory method. What does this do? Let's view the doc string. Takes a path to a directory and generates batches of augmented data. Now the arguments can be directory. So the first one, directory, that's what we've passed there. We might use the parameter name so we know. Directory equals train dir. Can be a string path to the target directory. Okay, beautiful. And if you keep reading, it's going to say that should contain a bunch of images. There we go. Any PNG, JPEG, or etc. images. And then the next thing we're going to pass in is batch size. So this equals 32. Now I believe by default it is equal to 32. Batch size 32. Batch size 32 is actually very common. You're going to see that a lot in the world of deep learning. But writing code, I will show you something. Google Yann LeCun batch size, and that's where you'll get 32 from. Target size equals, now this is the size we want all of our images to be. We saw when we imported one of our images that it was 512 by 512. But for our case, we want to reshape all of the images to be 224 by 224. You might be wondering, why this shape? Well, it's a very common shape to use. It also contains a certain amount of information. Say, a 512 by 512 image may have almost, or will have, over double the amount of information. However, 224 by 224 in practice still withholds a lot of the information within an image. Now again, you can mess around with this size to however you like, but this is a pretty good size for us to work with for now. The class mode we're going to be working with is binary. So that's telling our train data gen that we're importing data in a binary format. We're working with two classes. Then finally, we're going to pass seed equals 42 for reproducibility. We've covered a bunch of different parameters there fairly quickly. If you want to have a look into what each of them do, we can kind of deduce what they do from reading them here. But don't forget, you can read the documentation for this. We're going to keep going. You might have guessed, we also need to set up one for the test data, but this is going to be a little bit confusing. I'm calling it valid data, but that'll be clear in a moment as well. We're going to go valid data gen dot, this is coming from up here by the way, valid data gen dot flow from directory. You might have guessed we're going to pass in this directory. This is going to be the tester. The batch size is going to be 32. The target size, what shape do we want our images to load in? It's going to be the exact same as the training images. Same thing for class mode. It's going to be binary. And then the seed is going to equal 42. Wonderful. So what have we done so far? We've loaded our images. We've pre-processed our images using the image data generator class. Now we're going to build a CNN to find patterns in our images. Whew. We are covering a lot. So build a CNN model, and this is the same as Tiny VGG on the CNN Explainer website. If you want to skip ahead, you can Google the CNN Explainer website and check that out. We're actually going to have a look at that in a moment, but I'm just going to write the code to replicate the model on the CNN Explainer website, which is the Tiny VGG convolutional neural network architecture, which might not mean much to you for now, but we will see what it looks like in practice. So I'm going to set up a Keras sequential model, and then the first layer is going to be TF Keras layers conv 2D. The first parameter I'm going to pass here is filters. There will be 10. And the kernel size. Again, we've covered none of these, but we're going to see them soon. I just want you to get hands-on writing your first convolutional neural network as fast as possible. Activation equals ReLU. Then we're going to set up the input shape. Now, this is the input shape our first layer is going to take. It's going to take images in the form of 224 by 224 by 3. So that's what this pre-processing function is going to do. Reshape our images into 224, 224, and then also the 3 is going to be for color channels. So that's where that comes from. And now we're going to go into another layer. Let's have one of the exact same. So this is going to be TF Keras layers conv 2D, except this time we're not going to pass it any parameters. It's just going to be 10, 3, and then activation equals relu. Wonderful. This layer here is actually the exact same as this layer. If we look at the docstring here, it goes filters, kernel size, strides, the default is 1.1. Again, you're going to read all these and go, whoa, what is going on here, Daniel? We're writing convolutional neural networks from scratch. We'll go, oh, actually, not really from scratch. We're using TensorFlow to do so. Max pool 2D. This is coming directly from colored block addition. Pool size equals 2, and the padding here is going to equal valid. We haven't seen the max pool 2D layer, but that's okay. And now the tiny VGG architecture actually has 2 more convolutional layers. TF Keras layers conv 2D, 10, 3, activation equals relu. Oh, we've been using double apostrophe, so I'm going to keep it that way. Relu. And then it's going to have another convolutional layer, layers conv 2D. And then we're going to go 10, 3, activation equals relu. Wonderful. And then we're going to have another max pool. So TF Keras layers dot max pool 2D. You see the pattern we're sort of building up here? We can pass it 2 there. We've got 2 conv layers, then a max pool layer. 2 conv layers, then a max pool layer. Now we're going to have TF Keras layers flatten of the max pool layer before we pass it to the output layer, TF Keras dot layers dot dense 1, because we're using binary classification. Activation function is going to be sigmoid. Boom. Look at that. This is our first ever CNN model. I'm so excited, and I do know we did cover this very fast, but don't you worry. If you want to jump ahead and see what's going on here, I highly encourage you to search up the CNN Explainer website. But as I said, we're not leaving this Google Colab until we've built an end-to-end example. So this is our model. Now what do we do once we've built a model? Come up here. We've built CNN to find patterns in our images. Now we have to compile our CNN. So let's do that. Now this is something we've had practice with. Compile our CNN. I want you to have a think about it. What might our loss function be if we're doing a binary classification problem? What might our optimizer be? And if we're doing a classification problem, what's a good metric to begin with? So you might have already gone ahead and compiled our model, but if not, that's okay. Let's do it together. We're going to use binary cross entropy as a loss function because we're working with a binary classification problem. And let's set up our optimizer to be TF Keras optimizers.atom. Wonderful. And then we're going to set up the metrics. Now, because we're working in classification, accuracy is a good metric to start with. And then we're going to fit the model, history1 equals model1.fit. What do you think we can pass in here? If we came up here, where's our training data? Here we've got it. We've got it in a training data object. We've got validation data here too. So what we can do with the fit function is pass train data directly to that. And because train data is an image data generator class of the training directory, already pre-processed for us. So we can pass that straight to our neural network. And then we're going to fit it for 5 epochs. The beautiful thing about this class actually, flow from directory, is that it creates the data and labels automatically for us. So that's why we can pass it here, train data, without having to pass X and Y to .fit. The labels and data get created for us in this train data object. Then we can go epochs 5. We're going to introduce ourselves to another parameter here, which is steps per epoch. Steps per epoch is going to be len train data. So if we have a look at the length of our training data, oh, we can't see it there. I'm going to just comment this out, run this cell. There we go. So this is what outputs when we run these. It has found 1,500 images belonging to 2 classes and 500 images belonging to 2 classes. So this is the training data, 750 images per class. And this is the testing data, 250 images per class. And if we go len training data, 47 Now you might be wondering where that came from, but if we go 1500 divided by 32, because we've got a batch size of 32, what does that equal? 46.875. So now we have 47 batches of 32 images and their labels because there's 1500 total images. Now the reason we put things into batches is because that way it can all fit in memory of our computer chip. So if we tried to calculate the patterns on all images in one hit, our computer might run out of memory. But if we merge them or if we splice them into batches, it gives our computer a chance to calculate the patterns on the first 32 images, then the second 32, the third 32, and so on, to work out the patterns for the overall entire image data set. So if we come in here, that's why we wanted to go steps per epoch. We needed to do 47 steps per epoch. So 47 passes across the data, one for each batch. And then the validation data is going to be equal to the valid data. And then the validation steps, which is the same thing as steps per epoch, is going to be len valid data. Far out. Did we just cover a lot of ground or what? But I'm so excited because we're about to look at this all in one cell. This is what we've done. We've loaded our images. We've pre-processed our images. We've built a CNN to find patterns in our images. We've compiled our CNN. Now it's time to fit it to our training data. Do you reckon we've made a mistake? Are you ready to run it with me? I'll give you a second to catch up. If you need to write some code, that's okay. Finish writing out what's in this cell. I'll scroll up a little bit so you can see what's going on, but we're about to run it in 3, 2, 1. Your first convolutional neural network built by yourself. Or if you've done deep learning before, this might be another one, but the first one we've built together in this course, look at this. Oh my gosh, this is beautiful. It's fitting on the data. Epoch 1 of 5. Now we've got a fairly large ETA here. This is probably the longest ETA we've had to wait for. This is over a minute. What's going on here? Why is this taking so long? I might give you a guess. Why do you think this ETA is taking so long? I'll give you, it's nothing to do with the code we've written. It's actually to do with the runtime we're running. You see here, we're not using any kind of hardware acceleration. So we're trying to calculate all the patterns on our data without a GPU. So that's probably what we'll do in the next video, is we'll change our hardware to a GPU. I'll let this run for about 1 epoch, and you can do the same. You can actually let it run the whole time if you've got the patience to. But I'm going to stop mine after 1 epoch, and I'm going to come back in the next video and compare and see how much faster it runs with a GPU versus without a GPU, which is what we're doing now, running without a GPU. So let yours run for a little bit, at least 1 epoch, so you can see how long it goes for 1 epoch, and I'll see you in the next video, and we'll speed up this code.